Okay. Now one very simple application and a very useful application also, of this compactness theorem is the upward Lowenheim-Skolem theorem. Okay, what does this particular upward Lowenheim-Skolem theorem say? Suppose L is a predicate language and gamma an L theory. With an infinite model M. Okay. Then, if kappa is an infinite cardinal bigger equal the size of L, then M has, then gamma has a model N with size kappa. Okay, so very interesting result here. Okay, but now let us talk for a bit. So once we have, let's say, a dense linear order without endpoints, do you know any model? Rational numbers, real numbers, and now suppose you are interested in the question, does there exist? I mean, suppose your cardinality of interest is Aleph sub epsilon naught. You remember epsilon naught as an ordinal? Now you would like to know whether there is a model of this theory, dense linear order without endpoints. If there is a dense linear order without endpoints of cardinality Aleph sub epsilon naught. Yeah, then this theorem will guarantee the existence of this. Okay. So what we are doing here is that if you know that a model of certain cardinality exists, then you know that the model of any cardinality above that will also exist. Okay, so let us do another example. So this one also says, if you take your language to be empty, L set, then, and suppose you know that for a theory there is a model of cardinality Aleph naught, a countable model exists for a theory, then you know that there is a model of every cardinality. So essentially this upward Lowenheim-Skolem theorem says that you can, the class of models, if it contains one infinite structure, then it is a proper class, because for each cardinality there is a model. Yeah, eventually there is a model for each cardinality. That's what this says. And there is a very minor condition here which says that kappa is an infinite cardinal and it has to be at least as large as the size of the language. This is for a very silly reason. Yeah, because maybe, so assume that kappa is, size of L is 2 to the Aleph naught. Do you remember any language which has size 2 to the aleph naught? Huh? A language with size 2 to the aleph naught? The theory of R vector spaces, I mean the language of R vector spaces. There is one unary function symbol for each real number. So obviously that theory is very large, that language is large. It has 2 to the aleph naught many symbols, the rest of the symbols are countable. So 2 to the aleph naught plus a countable set, well that's done. And there is also essentially, all those function symbols, they act differently if your vector space is non-trivial. So obviously you shouldn't expect that there is a countable model. Can there exist a countable vector space, countable real vector space? Yeah, it doesn't make sense. Right? So therefore we have this silly restriction. Okay? In fact, this theorem is going to say something more, but I will first write down the proof of this, and the proof is actually very simple. And the technique that is used for such kinds of proofs, and that's a standard application technique for the compactness theorem, it's called expansion of language by constant symbols. So the idea, before we actually write down the proof, the idea is very simple, that you want a structure with size kappa, okay? You add one constant symbol, one new constant symbol for every ordinal less than kappa. So how many new constant symbols are you adding? Kappa many. And then you put more sentences in your theory. You already have gamma, and then you say whenever alpha and beta are distinct cardinals less than kappa, then C alpha and C beta are distinct. Their interpretations are different. This is our expansion of the theory. Once you have that, then you use the compactness theorem to show that it is finitely satisfiable, which we can do thanks to existence of an infinite model M, and then we are done. So we have a model of this entire theory where there are at least k kappa elements. You understand this? Let's do it. So, okay, perhaps, I remember this from a previous time. Perhaps I should say that with size of n at least kappa. Because the proof will not exactly guarantee that it's kappa. With the combination of upward and downward Lowenheim-Skolem theorem, we will get this exactly kappa. Okay, so consider the expansion L bar of L, where we add one constant symbol, well, I should say one new constant symbol, So you just make sure that it is a different name of the constant symbol, C alpha, for each alpha less than kappa. So here I would like you to recall some set theory, some cardinals. Kappa is a cardinal number, so it is an initial ordinal. So it's an ordinal in particular, it's a limit ordinal and it's an initial limit ordinal. So kappa less, like alpha less than kappa, is simply alpha belongs to kappa, all the elements. And how many elements are there in kappa? Kappa many. Okay, so I have added one new constant symbol, yes, for each ordinal alpha. And set gamma bar to be an L bar theory defined as gamma union negation C alpha equal to C beta, where alpha is not equal to beta and alpha and beta are less than kappa. Okay, we are going to claim that gamma bar is satisfiable. So if you want to show something is satisfiable, then what do? You show that it is finitely satisfiable by compactness. It is enough to show that gamma bar is finitely satisfiable. Okay, so let delta be a finite subset of gamma bar. Then the sentences in delta contain only finitely many new constant symbols. Can you see that? Gamma is totally new constant symbol free. Only these ones are the sentences which contain new constant symbols. So then the sentences in delta contain only finitely many new constant symbols. Say C alpha 1 dot C alpha n. Okay, then what can we say? Then delta is a subset of, we don't have any problem with gamma. We only needed to control the size of new sentences that are added. So negation C alpha I equal to C alpha j such that 1 is less equal I less than j less equal n. Do you agree with this? And have you seen some similar proof? You remember this? Proof of Koenig's lemma? Yeah, we added something new and then we want a finite subset of that. So it's a standard compactness theorem application. Okay, so delta is a subset of this. Okay. Then choosing C alpha I to be some element, okay, wait, let me write it more properly. So choosing C alpha I m, where 1 is less equal I, to be any finite subset of m. Yeah, so we are saying any finite subset of m where m is a model, an infinite model. See, why do we need it to be infinite? Because we want to interpret any finite number of distinct symbols as distinct elements. That's the only requirement. You understand? Okay, but if it were finite, let's say it had size 100, then for 101 new constant symbols, we couldn't really do this. We want, be any finite subset of M of size n. Okay, so all these constant symbols which appear in delta, we are interpreting them as distinct elements. Okay. We see that M satisfies gamma union this collection and hence M satisfies, M bar satisfies and hence M bar satisfies delta. Okay, I should make some changes, okay. M is a model, M is an L structure and M bar is an L bar structure. Where I have, we obtain, I should say, we obtain an L bar structure M bar. And we see that. So we simply took M, interpreted C alpha 1 as some element, C alpha 2 as another element. So because we just need to give interpretation of all the symbols. The only new symbols which we need to add are these. Okay. The rest of them don't really matter.
So the rest is same as in M.
Huh?
This rest is the one which comes from gamma is same as in M.
Don't say gamma. It's an L structure. So every symbol in L is interpreted just as in M. M as an L structure. And actually, I can be more technical and say that this is an intermediate language. Right? The intermediate language which consists of L and C alpha 1, C alpha 2, C alpha n. I can call it L prime and then I am defining an L prime structure here. But all I need to ensure, this can be made into an L bar structure also. All I need to ensure is that C alpha 1 and C alpha 2, they are interpreted as distinct symbols. So that M bar, this new structure, satisfies the right hand side and hence the left hand side. And we are done. Using just modifications of one infinite structure, we could prove this. Any questions? Your faces are blank. We don't have any hurry.
We proved it's an L bar structure, not an L structure.
We proved it's that L bar structure. So you interpret other constant symbols as anything apart from C alpha 1, C alpha 2, C alpha n. Other things are interpreted as anything. We don't really care. We only want that this one is satisfied.
No, I didn't understand how it's still a model of gamma.
It's a model of gamma bar. It's a model of that finite subset of this.
Yeah.
Are you confused why M bar is a model of gamma?
The end of the entire proof.
Yes.
No, if M bar is a model of gamma bar, why is it a model?
M bar is not a model of gamma bar. I am saying M bar is a model of gamma union these new finitely many sentences. It can't be a model of gamma bar. We want to find a model of gamma bar, but for that we use compactness.
Yeah, okay, so fine. Like suppose we found a model of gamma bar, why does it imply we found a model of gamma?
Oh, because gamma bar is gamma union something else.
No, but it's in a different language, right?
Yes, but by reduction of language again, Yeah, I mean you forget about all the new symbols. What's the confusion here?
Like, because it's a different language.
So therefore, okay, now let me write, this is the end of the proof of the claim. So, by compactness, let n, so there is a model n of gamma bar. Okay. So let's say there is a model n bar of gamma bar. Then what happens? Then thanks to, thanks to these sentences, negation C alpha equal to C beta for alpha and beta distinct and less than kappa, we know that then n bar satisfies negation C alpha equal to C beta, alpha not equal to beta, and alpha beta in like less than kappa. Right? So therefore, the universe n bar of n bar has at least kappa elements, kappa elements. Do you agree with this much? Okay. Now, just like we expanded the language, we can also reduce the language. So, let n be an L structure where the underlying universe is equal to n bar and each symbol in L is interpreted in N as the interpretation of that symbol in n bar. So this is called the L reduction of the L bar structure n bar. Okay, so for this, then what will happen? Then n satisfies gamma and n has size at least kappa. You get that? Every symbol was interpreted in exactly the same way. You simply forgot about the interpretation of the new constant symbols and you obtained n. So it's like, okay, consider this, natural numbers with order. Okay, we have natural numbers with orders. Now you add 0 to it. I mean, you have a language for orders and you add a constant symbol to it. So natural numbers less than and 0 is a structure. Then what is its reduction to the language which consists of only the constant symbol? Natural numbers comma 0. You simply forgot about less than. You can always forget some part of the language. Yeah, that's called reduction, reduced structure for that language. Is your doubt clear? Don't seem so confident. Okay.
So why do they have to be distinct? The interpretation has to be distinct.
No, interpretation doesn't have to be distinct. I just said that the interpretation is exactly the same.
Not here, back then when you said why n has to be interpretation of the new constant they have to be distinct.
The interpretation of the new constants has to be distinct because of these sentences. See that. When do you say, when do you say, so note that any structure K satisfies negation to C beta if and only if the interpretation of this in K is not equal to interpretation of this. Right? So therefore, for every distinct pair of constant symbols, new constant symbols, their interpretations are different, which means there are at least kappa many elements. Any problem? Feel free to ask more questions. I just want you to understand and get a feel of this. As you know, the proofs are not examinable. Right? Only the sentences are. Okay? So, let us do something different now. There is also a downward Lowenheim-Skolem theorem. Maybe I should state that first, and then we will not discuss the proof of it. It will be slightly complicated. Yeah, it uses some new terminology called Skolem functions, but we don't want to do that. But let me just state it. So downward Lowenheim-Skolem theorem. Okay. Suppose L is a predicate language. And gamma is a theory. M is an infinite model of cardinality model of I should say M is an infinite model of gamma with cardinality with size of M bigger equal size of L. Yeah, this is important again. Suppose mu is an infinite cardinal satisfying, mu lies between size of L and size of M. Okay, now I can see why my mu and M are the same. Okay, but this is, maybe I will use a different cardinal number, okay, that is better. Let me use little lambda. Okay, so suppose lambda is possibly a smaller cardinal, then there is some structure, then there is N, a model of gamma, such that N is a substructure of M. Okay, so I can find the substructure of of M, which is a model of gamma, such that the size of n is your prescribed size, lambda. So, for example, do you all know algebraically closed fields? Is there anybody who doesn't know? What is a field? Field has what is the structure? What is the language for fields? It is the language for rings. It has plus, dot, minus, 0 and 1. Okay. Then what are the field axioms? Associativity, commutativity, distributivity, identity. Then inverse for addition only. Yeah, I mean this associativity, commutativity and identity for both operations. And then finally the sentence. Yeah, I mean let me write down that sentence. So the theory. So let L ring be this language F, G, H, C, E. Yeah, this stands for plus, dot, minus, 0, 1. Okay. Then gamma ACF. Yeah, the theory of algebraically closed fields. Yeah, contains the axioms for a ring. Yeah, I am not going to write them down. Then the axiom that every non-zero element has. Right. So what is that axiom? Let's write down that for all W, if W is non-zero, then there exists a W prime such that GWW prime is equal to E and GW prime W is also equal to E. Yeah, so it has a multiplicative inverse. So this is the axiom. Now can you tell me, so far we have covered all the axioms for a field. Now we want to say that it is an algebraically closed field. How do we say that?
Add an axiom for every polynomial of degree n.
Add an axiom for every polynomial of degree n, and where are the coefficients coming from?
Just say there exists.
So normally if I want to say x square plus 1 x square plus 1 equal to 0 has a solution, I will say that there exists W such that W dot W plus 1 equal to 0. This formula is satisfiable. But what if I want to say that complex numbers are algebraically closed?
Yeah, for all W1, W2 there exists.
Exactly. So the coefficients, the coefficients are also coming from the field. So you can also put a universal quantifier for the coefficients. Okay. So and for each n bigger equal 1, add the following axiom. What is that axiom? For all W1, for all W2, dot 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 W, perhaps I should say for all W0 onwards, I don't want to say start at 1. For all W0, W1, dot 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 wn and w. So w is going to be our variable of the polynomial, one variable polynomial, and w0 is the constant coefficient, w1 is the coefficient of w, this is coefficient of w square and this is coefficient of wn. Okay, so we are going to say if wn is non-zero, then just a moment, I think I shouldn't write it over here. Yes, for all these coefficients, if wn is non-zero, then there is a w such that, now I am not going to use the complicated notation fgh, yeah, I am just going to write the polynomial in ordinary form, such that wn w to the power n plus wn minus 1 w to the power n minus 1 plus dot 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 w1 w plus w is w0 is equal to 0 and complete. So it says that every non-zero polynomial, every polynomial of degree n, yeah, degree n is ensured by saying wn is non-zero. Every polynomial of degree n has a root. You understand? Okay. So you add these axioms. So this is not a finite list of axioms. We are adding one axiom for each n bigger equal 1. Okay. So now we have got this theory of the theory of algebraically closed fields. Okay. Now, what is a model of the theory of algebraically closed fields? Now note that complex numbers, yeah, with plus, dot, minus, 0, 1 is a model of gamma ACF. Okay. And what is the cardinality of complex numbers? 2 power aleph naught. Okay. And what is cardinality of L ring? Well, 5. Yeah, there is nothing to think about. Only 5 symbols exist there, so 5 cardinality. So for any infinite cardinal, therefore, for an infinite cardinal, lambda less than or equal to size of the complex numbers, say lambda equal to aleph naught. We know that it is strictly smaller. There is a model of gamma ACF with cardinality lambda. Okay, so now this is a question. Do you know if there exists a countable algebraically closed field? By this theorem, yes, but otherwise do you know that? We have already seen a hint of this in our course. You remember there was one particular tutorial problem where I asked you to show that all algebraic numbers are countable, countably many. What is an algebraic number? It is a solution of a polynomial equation with integer coefficients. You remember that? What is an integer coefficient? I can use this language to write down any polynomial with integer coefficient, because if I want to say minus 5x square plus 3x plus 2, I can say 1 plus 1 plus 1 5 times, then put a minus sign because minus exists in my language, and then I can say multiplied by x and add 3x. So with integer coefficients, I don't even need to add this first string of quantifiers, this one. Okay, integer coefficients, you can write them down very easily. You are not asking whether there is a solution of the polynomial pi x plus 3 equal to 0. You are asking for something very simple. And you have shown that the set of algebraic numbers is countable. In fact, the set of algebraic numbers forms this. This is a model. Yeah. So the set of algebraic numbers, say it is usually denoted q alg bar. Okay. This is countably infinite, and this q alg bar is also an algebraically closed field. And the proof of the downward Lowenheim-Skolem theorem will actually generate this. What it does, I will give you some sketch of the proof in this case. You start with one polynomial equation. Okay? Then if it has a solution, then you add that solution. You start with a countable set, let's say integers. You always know integers do exist. Yeah? So you start with countable subset of C. Any countable subset would do actually. Yeah, but I am starting with integers. Then I write down all polynomial equations in with coefficients from the chosen set Z. Then if that polynomial has a solution, I can list all of them, right? Yeah. So step one by one, I ask whether this formula has a solution. If it has a solution, then I will add one solution using axiom of choice for each of those formulas to my set. So I keep increasing my set. Okay? And once I have done that, I repeat the process, because now maybe I have added root 2, x square plus 2 minus 2 is equal to 0. I have added root 2, but now I also want to make sure that because of this property, that a polynomial with coefficient root 2 also has a solution. So I repeat the process with newly found coefficients. And again I keep doing that countably many times, and after that whatever union of sets I obtain, that will be my gamma SCF, this q alg bar. Okay, that's how you prove the statement. Prove downward Lowenheim-Skolem theorem. Yeah, in fact this is not the only model, only countable model. I'll give you more, but tomorrow.